Hello students! This lesson is the first lesson on a series of 2 about trigonometric identities. This first slide is a review of the trig identities that we have discussed thus far in this course. Over in this column we have a summary of what I'm calling the basic trig identities. We can think of sine and cosine as the 2 foundational trig functions, and the other 4 trig functions can be expressed in terms of them. Recall that the tangent of an angle is equal to the ratio of the sine of that angle divided by the cosine of that angle. The cosecant of an angle is the reciprocal of the sine of that angle. The secant of an angle is the reciprocal of the cosine of that same angle. And the cotangent of an angle can be found by dividing cosine of that same angle by sine of that same angle. Furthermore, since secant is the reciprocal of cosine, then we can say up here that cosine is the reciprocal of secant. Similarly, since cosecant is the reciprocal of sine, we can say that sine is the reciprocal of cosecant. And lastly, tangent and cotangent are reciprocals of each other. So tangent is equal to 1 over cotangent, and cotangent is equal to 1 over tangent of the same angle. Now notice this numbering over here. I've numbered these basic trig identities as identities 1, 2, 3, and 4. This numbering corresponds to the identities that can be found on this summary sheet of all the trigonometric identities that we will discuss in this course, and then more. So identity 1, 2, 3, and 4 listed here under basic trig identities. Now through this lesson and the next lesson, we will review many of the identities that are found on this summary sheet. The summary sheet does include more identities than we will discuss officially in this course. We've also reviewed the Pythagorean identity, which is that for any angle, theta, the sine of that angle and then squared plus the cosine of that angle that's squared will always be equal to 1. That's because, given any reference triangle, as drawn here for an acute angle, the sine of this angle would be b over c, opposite over hypotenuse, and then square that, plus the cosine, which is adjacent over hypotenuse, and square that this will equal b squared over c squared plus a squared over c squared, and these have a common denominator, so they can be expressed as a single fraction, and a squared plus b squared, according to the Pythagorean theorem, is also c squared. So we get 1 out of this. This is why this is called the Pythagorean identity. Now keep in mind that when you put a power on a trig function in this position, the order of operations is to do sine of theta and then square the result, so cosine of theta and then square the result, and as long as theta is the same, then this sum will always simplify to just 1. Turns out this is also true if theta is any other kind of angle, including obtuse angles or negative angles. Now if you take this identity and divide both sides by sine squared of theta, and on the left that means you can divide each term by sine squared theta, you get the following result. We have sine squared over sine squared is 1. The power 2 can be pulled outside the fraction, and in this case as well, because when you square 1, you get 1 still, and then square sine of theta, you get sine squared theta. Recall that if you have a fraction and you raise it to a power, that power will affect both the numerator and the denominator. But now using our basic identities, cosine divided by sine is just cotangent, so this will be cotangent squared of theta, and 1 divided by sine is cosecant, so we'll get cosecant squared of theta. And this is the identity on our summary sheet that is numbered identity 7, listed right here. And then if you take identity 7 and subtract 1 from both sides, you get this variant of it. Or if you take identity 7 and subtract cotangent squared from both sides, you get this variant of it. If you take identity 5 and divide everything by cosine squared instead, you will get sine over cosine, which is tangent of theta, and that needs to be squared, plus cosine squared over itself is just 1, and 1 over cosine squared is 1 over cosine in parentheses squared, which is secant squared of theta. This is identity 6 on our summary sheet, found right here. If you take identity 6 and subtract 1 from both sides, you get this variant. Or if you take identity 6 and subtract tangent squared from both sides, you get this variant. Also identity 5, which is the traditional Pythagorean identity, you can subtract cosine squared from both sides to get this variant, or you can subtract sine squared from both sides to get this variant. And this collection of 3 identities and their variants form the class of identities that we call the Pythagorean identities. Notice that some of the identities are in boxes. It is recommended that moving forward in mathematics that you memorize all the boxed identities. They are used so often in both this class and in later math classes that it would be beneficial to memorize all boxed identities. Okay, let's go to the next page. Recall that a function is even if f of negative x is equal to f of x, and even functions are symmetric about the y-axis. Well, using this idea of symmetry alone, it's easy to see that the graph of cosine of x would be an even function, because if you take the right half of it and reflect it around the y-axis, you would get the left half of the graph, and the y-axis is an axis of symmetry. Furthermore, the reciprocal of the cosine function, which is the secant function, is also an even function. Again, you see symmetry about the y-axis. If you take the right half and reflect it around the y-axis, you get the left half, and together we have that symmetry. This means that the cosine of negative x is equal to just the cosine of x, and the secant of negative x is just the same thing as secant of x. So the argument could be positive or negative, and the results will be the same. Let's look at cosine of pi thirds. Using the unit circle to help us, we rotate from the positive x-axis pi thirds counterclockwise, and the cosine is the first coordinate, 1/2. But if we do that same rotation but clockwise, so in other words, do negative pi thirds, and the first coordinate is the cosine, and that's still positive 1/2. And in general, if you rotate any amount counterclockwise, so a positive angle such as 5 pi 6, and then instead rotate clockwise using a negative angle, but that same amount, that'll take us to points on the unit circle that are on the same vertical line. In other words, they have the same first coordinate, which is the x-coordinate. Thus, the cosine of both these angles is the same. So for cosine, it doesn't matter if you rotate clockwise or counterclockwise, you're going to get the same result, as long as the two rotations are identical, other than the fact that one is clockwise and one is counterclockwise. Now, a function is odd if f of negative x equals negative f of x. Odd functions are symmetric about the origin, meaning that there's a rotational symmetry 180 degrees about the origin. The graph of sine of x is an example of a function that's symmetric about the origin. If you take the graph of sine of x and rotate it 180 degrees, you get a graph that's identical to the original graph. Or if you plug in any x value and you get a y value, and then you plug in the opposite x value, you should get the opposite y value. This is what it means when we say that f of negative x is equal to negative f of x. Change the sign of the x-coordinate, and you can predictably get the opposite signed y-coordinate. The symmetry about the origin can also be thought of as a double reflection. If you take the right half of it and reflect across the y-axis, you'll get this. But then take that red graph and reflect that across the x-axis, then the graphs will align. So either rotate the graph 180 degrees about the origin, or do a double reflection, the first reflection across the y-axis and the second reflection across the x-axis, and if the graph lines up in either way, then we have an odd symmetry. The graph of cosecant has an odd symmetry. The graph of tangent has an odd symmetry, and the graph of cotangent has an odd symmetry. So because odd functions satisfy f of negative x equals negative f of x, then we know that sine of negative x will be equal to negative sine of x, cosecant of negative x will be equal to negative cosecant of x, tangent of negative x will be equal to negative tangent of x, and cotangent of negative x will be equal to negative cotangent of x. These are the four odd trig functions, and these are the two even trig functions. Let's consider the sine of pi thirds. If we rotate counterclockwise pi thirds, we get to these angles, and the sine is the second coordinate, which is the y-coordinate. And because we're in the first quadrant, that's expected to be positive. But if we rotate by the same amount pi thirds, but clockwise, so our angle is negative pi thirds, and the second coordinate, as expected due to the symmetry of this circle, should be the same answer but negative. So input one angle and get an output, input the opposite signed angle, and you should expect the opposite signed output. Or we can say more formally that the sine of a negative angle will always be equal to the negative of the sine of its positive version, which also confirms that we get negative radical 3 over 2. And you can see I've numbered 3 of these identities as identities 8, 9, and 10, shown here in my summary. Not every identity here is numbered, so you can think of me as just numbering the identities I view as most important, and then of those numbered ones, I have boxed the ones that are even more important moving forward in mathematics. Okay, let's go on to the next slide. Creating new identities. Express the following expressions in other ways. Because of the basic identities and the even odd identities and the Pythagorean identity that we've learned so far, we can actually manipulate expressions involving trig in lots of ways. For example, I can leave tangent as it is, but I know cosecant is 1 over sine. So multiplying this we get tangent of x divided by sine of x. But I also know tangent is sine of x over cosine of x. So I could change that only, and then multiply this together, and write my trig expression this way. Or I could change both. Tangent of x is sine of x over cosine of x, and cosecant of x is 1 over sine of x. And now we get a cancellation of the sines, giving me a 1 over cosine of x as a result. But that's also just secant of x. So this original expression can be written in any of these ways. They're all the same. This next one, I could leave cosine the same, but I could change the sine to 1 over cosecant of alpha, and then I could rewrite this by multiplying top and bottom by cosecant of alpha, and then distributing this cosecant to this fraction and to that 1. So I get in the numerator the product of cosine and cosecant, and in the denominator I get cosecant of alpha minus 1. So the original expression and this expression are the same. Another thing I could do is multiply the original, numerator and denominator, by the conjugate of the denominator, which is the same expression but addition. So my numerators I'll multiply, but I will not distribute. But for the denominators, I will do the FOIL process. So I'll distribute the 1 and then the negative sine alpha. So we get 1 plus sine alpha minus sine alpha, and then negative sine alpha times positive sine alpha will give me this negative sine squared of alpha. Now these two middle terms will cancel, giving me this expression. And now I can make use of a variant of identity 5 that says that 1 minus sine squared of an angle is equal to cosine squared of that angle. And now, just like x over x squared would simplify to 1 over x, I can cancel this cosine of alpha with the square, or one of the two cosine of alphas down in the denominator, giving me a final simplification of 1 plus sine alpha over cosine alpha. So the original is equal to this. It's also equal to this. And so we've created new identities, but these identities aren't so important that they're worth putting on our summary. In our first example, all 4 expressions in the pink boxes are the same, so we've created more identities. Okay, go to the next page. This page is about the sum and difference identities for cosine. Identity number 11, we're not going to prove that this identity is true, we're just going to take it for granted and then work with it, but it states that the cosine of a sum of angles, so the cosine of alpha plus beta, can be found by doing cosine of the first angle times cosine of the second angle minus, and then sine of the first angle times sine of the second angle. If you take identity 11 and you change all the betas to negative betas, then alpha plus negative beta will become alpha minus beta. The cosine of negative beta, cosine's an even function, so that just becomes cosine of beta again. But the sine of negative beta becomes the negative sine of beta, which is why this subtraction changed to addition. And that's because sine was an odd function. Well, that change makes identity 12, which is that the cosine of alpha minus beta is equal to cosine of the first angle times cosine of the second angle, but then plus sine of the first angle times sine of the second angle. These identities can be helpful in finding the value of sine and cosine at angles that are not traditionally on the unit circle. For example, let's find the cosine of 15 degrees without using technology. Well, first notice that 15 degrees is nowhere on our unit circle. It would be located right here, but what are the coordinates of this point on the unit circle? The first coordinate would be the cosine of that angle. Well, first note that we can arrive at 15 degrees by doing 45 degrees minus 30 degrees. And 45 and 30 are two angles that are on our unit circle. Thus, I'll be able to do the following. The cosine of 15 degrees is equal to the cosine of, and then 15 degrees is the same as 45 minus 30 degrees. And now I'm going to use identity 12, where alpha is 45 degrees and beta is 30 degrees. So we do cosine of the first angle times cosine of the second angle, and then plus sine of the first angle times sine of the second angle. I point out that when we have cosine of alpha plus beta, that this sign here is the opposite, subtraction. But when we do cosine of alpha minus beta, that we have addition here in our identity. Now I can use the unit circle to evaluate all 4 of these trig functions. The cosine of 45 degrees is rad 2 over 2. The cosine of 30 degrees is rad 3 over 2. Now multiply those and then add. The sine of 45 degrees is the second coordinate here, rad 2 over 2. And the sine of 30 degrees is the second coordinate right here, which is 1/2. And I multiply those two numbers. Now when you multiply two radicals, you can just multiply their radicands. That's because the radical of a times radical b is the same thing as the radical of ab. So I could multiply 2 and 3 and get 6 inside the radical. And then 2 times 2 is 4. And over here, rad 2 times 1 is just rad 2 over 4. These have the same denominator, so you could combine them into one fraction all over 4. Well, this result is what that first coordinate would be on our unit circle, when the angle is 15 degrees. We discussed the tools to get this missing second coordinate on the next page. I encourage you to confirm this with technology by grabbing a calculator and doing cosine of 15 degrees. Make sure you're in degree mode, and then also typing in this expression, rad 6 plus rad 2 all over 4, and you will see you get the same decimal representation, as shown here. Again, make sure that you are in degree mode. Okay, the next slide. These are the sum and difference identities for sine. Identity number 13 is that if you do the sine of alpha plus beta, that you can instead do sine of the first angle times cosine of the second angle, and then plus, which matches the plus there, cosine of the first angle times sine of the second angle. Now, we're not going to prove this identity. We'll just take it as true. And if you replace the betas with negative betas, then alpha plus negative beta just becomes alpha minus beta. The cosine of negative beta is just cosine of beta because cosine is an even function. And the sine of negative beta is the negative sine of beta because sine is an odd function, which is why we go from addition to subtraction here. And that gives us identity 14. The sine of alpha minus beta is the sine of alpha times the cosine of beta minus, and that matches the minus there, cosine of alpha times sine beta. Let's use one of these identities to help us with the sine of 75 degrees. Now, 75 degrees is not an angle on our unit circle, but it would be in this position, and the coordinates of that point are not known right now, but whatever the sine of 75 degrees is, that would be the second coordinate. Now, 75 degrees can be found by adding 45 and 30 degrees. And this is a good way to decompose 75 because 45 degrees and 30 degrees are two angles on our unit circle. Therefore, using the sine sum identity, we can say that 45 degrees will be the alpha and 30 degrees will be the beta. So we get sine of alpha, which is sine of 45 degrees, times cosine of beta, cosine of 30 degrees, and then plus cosine of alpha, so cosine of 45 degrees, times sine of beta, which is sine of 30 degrees. And now I can use the unit circle to evaluate all of these trig functions. Sine of 45 degrees is rad 2 over 2, cosine of 30 degrees is rad 3 over 2, plus cosine of 45 degrees is rad 2 over 2, and sine of 30 degrees is 1/2. This gives us radical 6 over 4 plus radical 2 over 4, which you could combine into one fraction. So this result would be this second coordinate here. To find the first coordinate, you would do a sum identity, but for cosine, which I won't do here on this slide. Okay, let's go to the next page. Here we have the sum and difference identities, but for tangent. Identity number 15. Again, we will not prove this. We will just take it as true. But the tangent of a sum of two angles, alpha plus beta, will be equal to the tangent of alpha plus the tangent of beta, and then all over 1 minus, and then the product of tangent alpha and tangent beta. And again, if you take all the betas and replace them with negative betas, then this alpha plus negative beta can be rewritten as just alpha minus beta. Tangent of negative beta, tangent is an odd function, so that's equal to negative tangent beta. And again, tangent of negative beta is negative tangent of beta, so this subtraction will become addition, giving us identity 16. Tangent of alpha minus beta is tangent of the first minus, that matches this sign here, tangent of the second angle, and then over 1 plus tangent of alpha, tangent beta. So in both of these identities, if this is plus, then that's plus, and this is the opposite. And if this is minus, then that's minus, and this is the opposite. Otherwise, the two identities are the same. Okay, let's do tangent of 13 pi twelfths. Now this one's in radians, but we have to figure out a way to decompose 13 pi twelfths into two angles, either addition or subtraction, where alpha and beta are angles on our unit circle. 13 pi twelfths is not an angle on our unit circle. And there might be multiple ways of doing this. Let's focus on trying to find two angles that add to be 13 pi twelfths. So let's decompose the 13 and experiment a little bit. I can break 13 down into 8 pi plus 5 pi and put these each over their own 12. Well, this angle is the same thing as 2 pi thirds. That angle is on our unit circle, but 5 pi twelfths is not. So this is not a useful decomposition. What about 9 pi plus 4 pi and then each over its own 12? Well, this simplifies to 9 and 12 are both divisible by 3, so we get 3 pi fourths. And 4 divides into 12 3 times, giving us pi thirds. This is a good decomposition because 3 pi fourths is an angle on our unit circle, and so is pi thirds. So we will find the tangent of 3 pi fourths plus pi thirds and use identity 15. So we do tangent of alpha, where alpha is 3 pi fourths, plus, and now we do tangent of beta, where beta is this pi thirds, and then all over 1 minus, and then the product of these two tangents. Now tangent of pi thirds. Tangent is sine divided by cosine. So we do the second coordinate divided by the first coordinate. And this simplifies to just rad 3. And tangent of 3 pi fourths, we do sine divided by cosine at this angle, so second coordinate divided by first coordinate, and this simplifies to negative 1. So the tangent of 3 pi fourths is negative 1, plus the tangent of pi thirds is radical 3, and then all over 1 minus, and then we do their product. Tangent of 3 pi fourths is negative 1, tangent of pi thirds is radical 3. This gives me negative 1 plus radical 3 over 1 plus radical 3. I encourage you to confirm this with technology. Make sure you're in radian mode, and we have that the tangent of 13 pi twelfths and the fraction negative 1 plus rad 3 all over 1 plus rad 3 have the same decimal representation. They are the same. And this concludes our first part of a two-part series on trigonometric identities.